So, well, without further ado, I want to introduce to you the first speaker. The second speaker. It's the first speaker after the break. So this is somebody who, well, wants to use everyday objects like clocks and scales and looks for them in the least likely place to find them in outer space. So be prepared to be warped within space-time. This is Jason Hessels. Give him a hand, please.
Hello. Okay. Thanks, Lucas. I don't think I can out-nerd Esther, so I won't even try. That's a compliment. Come on. You're right. So I'm going to talk about something I don't do in my spare time. I'm going to talk about something I do in 90% of my waking hours, which is work. And the bad news is I started preparing this talk this afternoon. And the good news is I've had 4 glasses of wine already. So this is just to wow you with my keynote skills. So this is where I work. I work in a place that's called ASTRON, which in itself sounds pretty nerdy. It stands for Astronomy Onderzoek Nederland, or in English, the name is Netherlands Institute for Radio Astronomy. It's in the metropolis of Dwingeloo in Drenthe. And this is what it looks like. And there are lots of nerds that work at ASTRON. There's also some geeks and some dweebs and some weirdos and spazzes and some borderline autistic people. This is where we're located. So I've circled Drenthe there. Drenthe, if you don't speak Dutch, is Dutch for nowhere. And ASTRON is located there. That's Neusendaal, and it's roughly in the middle of nowhere. We operate the Westerbork telescope, which you may have heard of before. It doesn't normally move that fast. And that was built in the 1970s. And oh, you can't see it very well, unfortunately. But this is our new high-tech telescope, which is a pretty amazing instrument, but it's unfortunately also a bit of a PR nightmare because it doesn't look like much. We built this giant circular island in the north of the Netherlands, in Drenthe, and we placed all these antennas there, and it's very high-tech. This is one of the this is one of the sheep pyramids that we use. These are all connected together, and all the signals are sent to a giant supercomputer, which can do all kinds of fantastic things, like triangulate sheep positions. But that's a bit of a distraction. The main thing I wanted to explain to you tonight is how to weigh a star using a clock, and specifically I wanted to talk about neutron stars because that's where my heart lies. But first I need to explain what's a neutron star. So first, how do you make a neutron star? How do you bake a neutron star? And very briefly, you basically you take a very massive star, something that has way more mass than our sun, something that's quite special in our galaxy, and that star eventually runs out of fuel. And at a certain point, once it's run out of fuel, it can no longer support itself against its own gravitational pull, and then you have the supernova explosion. And after the supernova explosion, you're left with this neutron star. And a neutron star is a very special thing. I'll explain why it's special in just a second. But it's also a very mysterious thing. And in some ways, it's very like frikandel, in the sense that one of the main questions about neutron stars and frikandel is basically what we want to answer here, and that's why we want to measure the mass of these stars to figure out how much horse meat is in there. So a neutron star is very, very small. That's our sun there. The Earth is about 100 times smaller than the sun, and then a neutron star is another 300 times smaller than the Earth. And remember, it's more massive than the sun, but it's 300 times smaller than the Earth. So it's very, very dense, and we'll come back to that in a second. It fits roughly, the diameter of a neutron star is roughly the diameter of the Mir, or maybe extended Amsterdam or so. So it's very, very small for a star. It's not that much. It's not that much less compact than. Well, it's almost a black hole, you could say. So here are some statistics about neutron stars. The radius is only about 12 kilometers or so. So like I said, about as big as the Mir. The mass is more massive than the sun. They have these really, really strong magnetic fields, and so much that, oh wait, I forgot to say something. So the radius is only 12 kilometers, and the mass is 1.4 solar masses. So that's a lot of mass. It's like 10 to the 30 kilograms or so. And that means that if you were to take a spoonful of mass from the top of a neutron star, which would be fairly difficult to do, but if you could do that, it would weigh more than everyone on Earth. Just to give you an idea. Now, they have very strong magnetic fields as well. About 1 trillion Gauss, or 1,000 trillion Gauss is probably the most magnetic one. And to give you a comparison, a fridge magnet is about 1 Gauss, or the Earth's magnetic field is about 1 Gauss. So this is about 1 trillion or 1,000 trillion times more magnetic. And they can also spin very fast. They can spin hundreds of times a second, maybe even up to 700 or maybe even 1,000 times a second. That's basically as fast as a kitchen blender. So you have a star, which is more massive than the sun, and it's spinning faster than a blender. It weighs, well, even a spoonful of it weighs more than everyone on Earth. It's a pretty interesting kitchen to do interesting tests of basic fundamental physical theories. Cost to ride? Did someone? What was the question? Well, okay, so I'll answer that ridiculous question. If you were to be anywhere near a neutron star, you would be squashed to basically the thickness of an atom or so. So it would, well, it doesn't matter much. Some neutron stars are pulsars, and this is important for this talk. You can see the neutron star at the center there, and as I explain this, I will get my model. So this is the model. So the neutron star is at the center here. That's the styrofoam ball, and then the pipe cleaners. Those are magnetic field lines, and they're like a dipole, so like a normal magnet with a north and a south pole. And you have these beams of radiation which are coming from the north and the south poles, and it's kind of like a lighthouse in the sense that as the star is spinning, sometimes that beam is pointing towards you. And when that beam points towards you, you see this kind of this pulse of radio light. And this is very important in terms of using this kind of star as a clock. So pulsars have been on a famous record before. These are pulses, individual pulses from the first pulsar that was ever found back in 1967. People won the Nobel Prize for that. Unfortunately, the woman who discovered them did not get the Nobel Prize, but that's a bit of astropolitics. And this is what a pulsar sounds like. So what we've done here is we've taken data with the Westerbork telescope and we've converted it into a sound. So we've basically taken the waveform and converted that into a sound. And the important thing to take out of this is how regular it is. So remember, we want to use these things as a clock. And yeah, they're very, very regular repeating objects, right? So we want to use these as precision clocks, and that's what we'll come back to. And actually, some of these things are as precise as an atomic clock, which is pretty cool. So how do we observe these? Well, you need a radio telescope to observe most of these, and you need a really, really big radio telescope because these things are really, really, really faint. So this radio telescope is in Green Bank, West Virginia, which is a very beautiful place. And it's about 100 meters across. This telescope is literally so big that you could not make a bigger telescope given the material properties of steel. So if you were to try and make a 200-meter telescope, it would just collapse under its own weight. You'd need to make it out of, I don't know, carbon nanotubes or something like that. So you use a telescope like this to observe a pulsar. You collect the pulses from the pulsar because you remember it's turning around. It's kind of like a lighthouse. It's sending these pulses out. And just for comparison, like I said, this is a really, really big thing. This is much bigger than the Statue of Liberty. It's almost as big as Washington Monument. I couldn't find anything in the Netherlands that is that big. Maybe the Euro Tower or whatever in Rotterdam. Oh, and by the way, if you want to buy me a glass of wine, I will tell you an interesting story about how they actually paid for that telescope. It's a sordid tale. So this is a predecessor of the Green Bank telescope. You can. This is on November 15th, 1988. You probably could have seen that already from the colors of the photo that it was in the 80s. And this is on November 16th, 1988. This is a bit of a side story, by the way. And some people say it was due to overuse of the telescope that the telescope finally collapsed after 30 years. But other people say, including the Weekly World News actually, that it was something a little more nefarious. And I tend to agree with that hypothesis. So now we move on to this idea of using pulsars as clocks. So we have these stars and they're pulsing very regularly, and we can use that to our advantage to try and figure something out, even though the star is very, very far away. We can't go there. We can't, like I said in the abstract of this document, you can't stick the star on a scale, but you still want to know how much it weighs, right? So what we have to do is we have to collect all these pulses from the star. We have to do all kinds of crazy data analysis stuff that I won't get into. And then we want to convert that information and kind of make a list of times where we know, okay, a pulse arrived at this time, a pulse arrived at that time, a pulse arrived at that time, so that we have an idea of how often this thing is spinning around. Because ultimately what you want to do is you want to make a model where you can put all kinds of interesting things about the star into your model. You want to know, for instance, where is the star? And if your model doesn't tell you where the star is properly, then what you'll actually see when you take that list of all those arrival times, you'll see something like on the top right there. You see that kind of sinusoid that's going up and down and up and down? That's because we don't know the position of the star very well. And as the Earth is going around the sun, every year you're getting this up and down motion. You're getting this sinusoid. So if you take that data and then you allow your model to fit for the position, for instance, you can get the position a lot more accurately, and that's interesting for lots of reasons. Or for instance, these stars are slowing down because they're losing energy. They have this magnetic field, and that's liberating energy. And for instance, if you're not calculating properly how fast the star is spinning down, then you'll see something like what's shown on the lower left there, where you get this kind of parabolic form. And that tells you that, oh, okay, well, your model isn't telling you how fast it's slowing down. So you can figure that out a lot more precisely. And the top left there, if your model tells you everything that the star is doing, then you don't see any residual effects anymore. You just see kind of noise. And this is a way that you can use a clock, basically, to find out very fundamental things, like how fast is the star slowing down. It tells you how much energy is being liberated, where the star is located. These are pretty fundamental things. To do this, incredibly, you need to, so you make measurements every once in a while. You can't always be looking at the star. You do this every few weeks or so, every few months. But in between each of those observations you do, your model has to be precise enough that you know exactly how many times the star has rotated in between those two observations. You don't want to miss even one turn of the star. That's pretty hard to do, but if you can do it properly, it's a really powerful method to study these objects. So some of these pulsars, they have a binary companion. They're orbiting around another star. It could be like a white dwarf star, which is another kind of compact star. It could be a star that's a little more like the sun. But the important thing is that they're moving around another object, and that's changing kind of the rate at which that we're seeing those pulses. It's kind of like a train that's passing by, the Doppler effect, because sometimes it's moving away from you and sometimes it's moving close to you. You see that the period, the rate at which all those pulses are arriving is changing with time. And very interestingly, there are effects, because these stars are so compact and they're kind of like black holes, they're warping space-time, and that's causing all kinds of strange effects that Einstein's theory of relativity predicted. It's causing all kinds of effects like that to become important, and that's also influencing how your clock is ticking. So basically it means that instead of having a normal clock, you have this screwed up wacky clock, which you can use to try and measure some of these effects, which is really interesting. So one of these effects, and one of these effects that you can use to figure out what the mass of the star is called a Shapiro delay, which is presumably named after some guy named Shapiro. So you see the pulsar there in the upper left, and then you see the companion star that is orbiting around there. And that companion star is massive enough that it's warping space-time. It's causing this kind of well. And then if we're lucky enough that the pulsar is kind of behind that companion at some point, from our point of view, that means that all those pulses that we're observing, they have to pass through that well, and they're being delayed by a certain amount. And if you can measure the arrival time when those pulses are coming to Earth with enough precision, then you can notice that kind of effect, right? So at a certain point, if the pulsar is in front of the other star, then it's not being delayed because those pulses don't have to go through that gravitational well. But if it's behind it, then those pulses do have to go through that gravitational well, and you should see that the pulses are coming later than when the pulsar is in front of the companion. Or to show it another way, so basically when the pulsar is in front of the companion, and you can see the line of sight to the Earth, for instance, the pulses are arriving at a certain time, but then when the pulsar is behind the companion, then there's quite a bit of a delay. And when I say quite a bit, it's maybe say 10 microseconds or 40 microseconds. You have to do pretty precise measurements to actually notice this. But it's a very interesting effect because the amount of that delay, so how deep that gravitational well is, it depends on how deep, how massive that companion star is. Right? So if the companion star is also really, really massive, then it's going to bend space-time more. It's going to cause a deeper well, and those pulses are going to be delayed more. And this tells you something about the system itself. So, for instance, we did these measurements with this Green Bank telescope, which I showed before, the new one, not the old one. Thank you. And what you see here is you're making measurements of when those pulses arrive at different times when the pulsar is moving around the companion star. And you're seeing, relative to the other measurements you made, is it arriving earlier, is it arriving later? And what you see is those red points there, which at a certain point, which happens to be when the pulsar is behind its companion, you're arriving really, really late, right? So we can fit that, try and figure out how massive that companion star is. And in turn, that actually tells us how massive the pulsar itself is. So this is a way that you can use the clock-like properties of a neutron star to infer how much it weighs, which would be impossible otherwise, right? So in that model, you're able to figure out how much the neutron star weighs. And this is something that we call the equation of state, which sounds very fancy and very learned. But in fact, all it means is, if the star weighs this much, if it has this much mass, how big is it? That's all that means, actually. As a function of the mass, what is the radius? How big is it? Or you could also say, if it's this big, what is the mass? And we think that there's some kind of unique relation. There's some kind of line that you can plot as a function of mass and radius that describes, what a neutron star looks like. And that's what all these little lines are, all the blue lines, all the green lines, all the pink lines. Those are just different people's guesses at what this might be. And people make entire careers on making these guesses. Not me, though. And then what you see is, there's certain areas of this diagram which are excluded. Some things are impossible just because, if the star was that massive and that small, then it would just collapse into a black hole, for instance. That showed in the upper left-hand corner. But what you see is if you find a star that's really, really massive, like, for instance, the one I showed on the last slide, that's that kind of red bar that's going across there horizontally. If you find a star that's, say, in this case, 2 solar masses, there's a lot of models that say, well, I don't think I can make a 2 solar mass star. So those people have to retire. And you end up with a better idea of what the star is made of, because you have a closer idea of which models are better approximating what's actually happening in nature. And this, of course, is interesting because remember, pulsars are, or the interiors of pulsars at least, are like fricandel. They're very, very mysterious. We have no idea what's inside. There's some people who think that pulsars are basically made out of neutrons. That's why they're called neutron stars. There's some people who think they're even more exotic, that maybe they're made of what are called free quarks. So all the quarks that make up a neutron are free to move around and interact with each other. You end up with something called a strange star. It's a very nice name. So that's strange matter, and then, well, it's fricandel is very strange matter. But doing these kind of measurements, that gives us a better idea of what's actually inside. And we still don't know for sure, but the important thing is figuring out which models are correct, which models are not correct, and ultimately trying to learn something about particle physics, trying to learn how does matter interact when it's really squashed together very, very, very closely. So, I think I'm going to end it there, and thank you very much, and ask for questions.
So thanks very much, Jason. I see people even camp here in the front of the audience to hear your story better. It's really nice. So, questions? Please raise your hand if you have one. Over there?
What is your job at the...
Do you make fricadelles?
Yeah, well, so my job is to get the telescope that I showed earlier, the PR disaster. My job is to basically get this telescope, the Loeffler telescope, working, because we think that there are a lot of pulsars in the galaxy that we haven't discovered yet, because they're really, really faint. They're not easy to see. But we think with this telescope it's going to be possible to find them. So we basically want to find all of these pulsars, and if you find, say, 1,000 of them, most of them are going to be pretty boring. It's kind of like people. But there's a few that are going to be really, really interesting and very, very special. And those are the ones that will tell us something new scientifically, right? It's always the things that stick out that you can learn from, right? So that's my job. That's what I do 90% of my waking hours.
Another question? Richard here?
Yeah, he knows my name by now. Yeah, and then sounds like a stupid question, but how do you actually decouple like rotational speed from angle? I mean, you just have this like beep, 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 beep. You don't know what angle the star is and what speed it's going, right?
Well, you kind of do know what the angle is because the pulses themselves are very narrow, so they don't occupy a very... That has nothing to do with the answer. I was going to show you... Yeah, the pulses themselves are very narrow, so what's being plotted here is what we call pulse longitude. So how much, so 360 degrees is one turn all the way around. And the pulses are only a very narrow range, right? So you kind of use that as a fiducial point to say whenever we hear a pulse, we know that the star is facing us, and wherever we don't, we don't. And if it was something more like a sinusoid, you wouldn't be able to do that nearly as precisely, right? So that's the main reason.
No more questions? Okay, well, let's thank you, Jason, again. Thank you very much, and thanks all for coming. We will have a continuation of our celebration of being nerds at the 30th of June here. I know because you're all nerds, you don't go on holidays, so you will certainly all be here. Yeah, so that was it for tonight. DJ Book Tunes will play you some more songs. I am Lucas Ellerbroek, and thanks for coming.